And
hello.
Okay, so the next session, the subject is Axiomatizing Consciousness, Setting and Postulates. And to have the talk, we have with us a live video lecture, Professor Henk Barendregt, Radboud University, Nijmegen and the Netherlands. So before I start, I would like to tell you that any kind of queries, any kind of questions in your mind, you can do WhatsApp on this number, that is 8240-819460. If you want to question, if you want to drop any kind of question, you can drop in this WhatsApp number. Again, I want to announce 8240-819460 in this screen, you can see. And before I start, I would like to introduce Professor Henk Barendregt. Professor Henk occupies the chair of Foundations of Mathematics and Computer Science at Nijmegen University, the Netherlands. Since 1986, he is professor at Nijmegen University, where he and his group work on formal mathematics or technology based on the idea of automated verification of mathematics program of N.G. de Bruijn. Barendregt was elected member of the Academia Europea in 1992 and the Royal Dutch Academy of Sciences in 1997. In 2002, he was knighted in the Order van de Nederlandse Leeuw. Barendregt obtained on February 6, 2003, the NWO Sponsor Award 2002, the highest scientific award in the Netherlands. For some years, Mr. Barendregt has been studying consciousness. In 2012, he obtained the Distinguished Lawrence Fellowship, a joint prize by the Netherlands Institute of Advanced Studies and the Lawrence Center, Leiden, organizing a workshop on the models of consciousness and clinical implications. So, Professor Henk is on live video chat with you, and here is the lecture. Enjoy, and any kind of queries, any kind of question you want to ask, here is the number on the screen. You can ask him in the WhatsApp number. Thank you so much and enjoy his lecture. Thank you.
Good afternoon. I'd like to thank the organizers of the Bhaktivedanta Institute for inviting me to this conference on mathematics and reality. And as an important aspect of reality is how it comes to us, how we perceive it, I would like to speak about consciousness. Now, there is a problem with consciousness. When we try to imitate human beings, then we can think of a robot that can move and it has a camera and a microphone. But do we miss something? Well, it is not the intentions that humans can have or the emotions that humans can have that are the problem. What seems lacking is the awareness, consciousness in a robot. And we do not even know what it means that they would have consciousness. In the axiomatic method of Aristotle, we do not need to explain the primitive notions. We just use them. So I will use consciousness as a primitive notion. And the method is built up from relationships between several of the primitive notions, and that are postulated to hold axiomatically. And in this way, we try to give various approximations to consciousness. And we will describe several classes of agents in order to do this. An agent A lives in a world which is its environment. So the world W and A, they both have a state for each moment t in time. So we have W, t, and A, t. Then the world and the agent interact. So the world at moment t and the agent at moment t, here you see it, they interact and they create the world in the next moment and the agent in the next moment, somewhat changed. And this will take some time. And then the new states interact again and again. So here, axiomatically, we want to make time the discrete set of integers, z, the negative, 0, and positive numbers. We will describe 5 classes of agents. It's a hierarchy, and they will get more and more complexity. Starting with Turing machines, then robots, then agents with priorities. We can think of animals, then agents with cognition. We can think of higher animals, and then finally agents with mindfulness. And we can think of human beings. And class 5 is intended to approximate aspects of consciousness. Now first, the Turing machines. A Turing machine has an infinite tape of cells as its world, and they are numbered by the integers. Each cell may contain a 0 or a 1, and then there is a reading and writing head located on one of these cells. Depending on what the agent reads and what is its state, there are 3 actions performed: writing a 0 or 1, changing the state, and moving the head to the left, to the right, or neither of the two. And these actions can be written down in a fixed finite list of 5 tuples that is fixed for each Turing machine. The initial content of the tape represents the input, and if the machine stops, the final content, the output. Now, Alan Turing in 1937 showed, using introspection for the first item, that any computational job can be done by some Turing machine. However, there is a universal Turing machine, UM, that can imitate all the other Turing machines by extra input on the tape. And nowadays, everybody knows this. We need also software to run a computer, and that's the extra input. Then Turing showed that there is an unsolvable problem about the universal Turing machine. Does this machine with input X and extra input X, so the program, does that stop? That's the famous halting problem. And in this way, he showed that computers cannot solve all human problems, not even human problems about mathematics that are very clearly defined. Leibniz, when he was thinking about machines, he wanted to ask to the machine, does God exist? But this question is out of reach, and even mathematical questions are out of reach, as Turing showed. But the universal machine became the programmable computer. The next class of agents are robots. They have sensors and actuators connected to special parts of the memory. A simple example consists of a thermostat with a heater or an air conditioner switch to regulate the temperature in a room. More advanced robots are embodied and move around in the world. A simple example is one that vacuum cleans the floor and goes to the electric outlet if the battery is low. Such machines we have now. Now, once you are in the world is part of the memory. And when you mimic the Turing machine description, a robot originally would act as follows. You have an input, the I, and a state, the S, and then you come into a new state and then a new action. And then because of the action, you're in a different place of the world, so you have new input and you already had a new state. And this goes on and on. But now it's better because of the embodiment to write things as triples, input, state, and the action. And it gives the next input, the next state, and the next action. We do not want to wait till we see what we did, but from the doing itself, we calculate the next state and action. Now, in the next class of agents, the input is not a single bit or byte, but a large collection of these. Think of it for yourself. Not only you may be looking at screen, but you see other aspects of this room. And you hear my voice, but you also may hear other things. But then there is the mechanism of focus, of attention, that selects a subset of these. And this F selects a subset of all the things that are present to you, I1 till IN. All those inputs are there, but you select only some of them. And in the same way, you have several actions possible, so A1 till AM, but G selects a subset of them. And this is good to have, especially for us animals, because we can give priorities to some of the actions. You have decided to come to this conference, sit here and listen. Now, because of the complexity of the data, the transitions are no longer to be found in a finite table, because there is so much to react on. And now it is more efficient to implement a function f that calculates how to go to the next triple. So we have a certain input, a certain state, and already we have a certain action. We sit here and listen or speak respectively. And the function computes what to do next. And in MLs, this is computed by an artificial neural net. Interestingly, this introduces errors, discrepancies between the performed action and the agent's intention. But there are also other sources of errors, like the presence of other agents in the world. And what is a success of an animal? That means that it can reduce errors. Now, also agents in A3 will be given a rudimentary memory, notably associative memory. And this is given in the form of cued recall, something that has been studied already in early experimental psychology, namely in 1858, quite early. During the learning phase, input I1 is followed by I2. And we repeat this a couple of times. And then during recall phase, only E1 is I1, I mean, is presented, and the agent will then remember I2 and can react accordingly. For example, if earlier on the animal has learned that a certain sound means danger, then now from the sound only, the animal can start running away to safety.